We'll use three main strategies to solve the exponential and logarithmic equations we'll encounter. For each, we'll use the rules and properties of logarithms and exponents. Often we'll find that we can solve exponential equations by taking the logarithm of both sides. And for our logarithmic equations, it will be helpful to change them to exponential form. Let's take a look at these two exponential equations. This first one you probably recognize, 2 to the power of x equals 8. You can probably solve that one in your head and won't need a calculator. But we'll use this one to show how using the rules of logarithms, how using the strategies on the previous slide can help us solve exponential equations. One strategy is to take the logarithm of both sides of an exponential equation. In this case, we'll take the logarithm of 2 to the power of x and the logarithm of 8. In both cases, I've chosen to take the logarithm to the base 10 because I can evaluate logarithm to the base 10 using my calculator. Now that we have the logarithm of 2 to the power of x, we can use the properties of logarithms to simplify. We can take the power and move it out front to become a multiple of logs. This gives us x times the logarithm of 2 is equal to the logarithm of 8. Now that we have a multiple of logs, x times the logarithm of 2, I can isolate the x simply by dividing both sides by the logarithm of 2. Dividing the left side by the logarithm of 2 will isolate x, and then I can calculate the logarithm of 8 divided by the logarithm of 2 using my calculator. This gives us x is equal to 3. Usually we'll have a decimal here. If we have a nice number like this, we probably could have solved this problem without turning to our calculators. Another way to solve the same problem is to start with the exponential form, 2x is equal to 8, and convert this exponential equation to its logarithmic form. In other words, write it as the logarithm of 8 to the base 2 is equal to x. Now, my calculator can't calculate the logarithm of 8 to the base 2, but here I can use the change of base equation. Start. So I can write this as x is equal to the logarithm of 8 to the base 2. Now I can't calculate the logarithm of 8 to the base 2 using my calculator, so I'll have to change the base. I'll change it to the logarithm of base 10. So I get x is equal to the logarithm of 8 to the base 10 divided by the logarithm of 2 to the base 10. That's simply using the change of base equation. And we've seen this before. We've already evaluated the logarithm of 8 divided by the logarithm of 2. We know that this is equal. Both strategies yield the same answer, so choose the one that you find easiest. Let's try the first strategy again for the second question. We have 3 to the power of negative x is equal to 0.525. This is one that doesn't have an integer answer, so we will have to use our calculators. Let's try taking the logarithm of both sides. Again, I'll take the logarithm to the base 10 of both sides, since I can use my calculator to evaluate these. So the logarithm of 3 to the power of negative x is on the left-hand side, and on the right, I'll take the logarithm of 0.525. Once again, I'll use the properties of logarithms to take the power and turn it into a multiple. This gives us negative x times the logarithm of 3 is equal to the logarithm of 0.525. Dividing both sides by the logarithm of 3 isolates the x. And in fact, I can get rid of the negative 1 in the same go by dividing by the negative logarithm of 3. So we've isolated x on the left-hand side. So we simply use our calculators to evaluate the logarithm of 0.525 and divide that by the logarithm, or the negative logarithm, of 3. We get a final answer here of 0.562. 0.685. You can try this question again by converting 3 to the power of negative x equals 0.525 to its logarithmic form. You should end up with the same answer. Let's try two more. On the left here, we have the logarithm of 3 to the power of x minus 2 equals 5. Let's once again take the logarithm. Let's once again take the logarithm of each side. On the left, we have the logarithm of 3 to the power of x minus 2. Of course, this is to the base 10. And on the right-hand side, we'll take the logarithm of 5 to the base 10. Properties of exponents. We have to make sure we take the whole power, so that's x minus 2, and turn that into a multiple. So we have x minus 2, and that's all of x minus 2, so I'm going to tuck that binomial into brackets, multiplied by the logarithm of 3 is equal to the logarithm of 5. Now here mathematically we have a couple options. We know that the guidelines for solving equations suggest that we open up any brackets when we can. So here that involves using distributive property. So we'll take the logarithm of 3 and multiply it by x, and then the logarithm of 3 is multiplied by negative 2. So we have x times the logarithm of 3 minus 2 times the logarithm of 3 is equal to the logarithm of 5. I'll isolate the term that the x is in by adding 2 times the logarithm of 3 to both sides. So we have x times the logarithm of 3 is equal to the logarithm of 5 plus 2 times the logarithm of 3. And now finally, x is being multiplied by the logarithm of 3, so I can isolate x by dividing both sides by the logarithm of 3. This leaves me with x on the left-hand side, and I calculate the logarithm of 5 plus 2 times the logarithm of 3 divided by the logarithm of 3 on my calculator, and I get 3.4650. Another option would have been to stop at this point and isolate the binomial that we find the x in. So at the point where I've indicated the star, we could have divided both sides by the logarithm of 3 to isolate the x minus 2, and then we would have isolated x by adding 2 to both sides. Try it. You should end up with the same answer. We've got one more problem, and this one you actually don't need a calculator for, so give it a shot first. 6 to the power of 2x is equal to 1. Can you solve that using the properties of exponents? For practice, let's try solving it by taking the logarithm of both sides. So on the left, we have the logarithm of 6 to the power of 2x, and that's logarithm to the base 10. And on the right, we'll take the logarithm of 1, also to the base 10. Using properties of exponents, we'll take our power and turn it into a multiple. So we have 2x times the logarithm of 6 is equal to the logarithm of 1. Maybe you're already noticing that because I have the logarithm of 1, this is a special logarithm, there's something going on here. Remember that if I'm taking the logarithm of 1 to the base 10, I'm asking the question, 10 raised to what power is equal to 1? 10 raised to what power is equal to 1? What power turns any base into 1? Well, 10 to the power of 0 is equal to 1. So the logarithm of 1 to the base 10, the logarithm of 1 to the base 10 is equal to 0. Let's carry on regardless. Because I'd like to isolate the x, I'm going to divide both sides by 2 as well as by the logarithm of 6. So I'll take this right-hand side and divide it by 2 times the logarithm of 6. This has isolated x on the left-hand side, and on the right-hand side, we find this is equal to 0. 6 to the power of 2 times 0, or 6 to the power of 0, is equal to 1. Again, we can show that x is equal to 0 using a number of different strategies here, including taking the logarithm of both sides.